Imagine two twins. One stays on Earth. The other boards a spacecraft and travels near the speed of light. When the traveling twin returns, only a few years have passed for them. But their sibling on Earth? They've aged 50 years. This isn't science fiction. This is time dilation, a proven, measured, unavoidable consequence of living in our universe. In 1971, scientists placed atomic clocks on commercial airplanes and flew them around the world. When the planes landed, the clocks showed different times than identical clocks that remained on the ground. The difference? A few hundred billionths of a second. Minuscule, but real. Time doesn't flow uniformly. It bends, it stretches, it breaks. Every GPS satellite orbiting Earth experiences time differently than you do right now. Without constant corrections for time dilation, your navigation would be wrong by miles within minutes. The technology in your pocket depends on Einstein being right about time being flexible. What if I told you that right now, at this very moment, you're traveling through time at a different rate than someone standing on a mountaintop? That gravity literally slows down time, that the ground beneath your feet ages slower than your head. Today, we journey through the evidence that time, the one thing we thought was constant, the bedrock of existence, is an illusion, a flexible dimension as malleable as space itself. Prepare yourselves. Reality is stranger than you imagine. We begin. In 1887, two American physicists, Albert Michelson and Edward Morley, conducted what should have been a straightforward experiment. They wanted to measure Earth's motion through the luminiferous aether, the invisible substance scientists believed filled space and carried light waves. Their apparatus was brilliantly simple. Split a beam of light, send the two beams perpendicular to each other, bounce them off mirrors, and recombine them. If Earth moved through the aether, one beam should travel faster than the other, creating an interference pattern. They found nothing, no difference. No matter which direction they pointed their apparatus, no matter what time of year they measured, light always traveled at exactly the same speed, 299,792,458 meters per second. Always, without exception. For nearly 2 decades, physicists struggled with this paradox. The answer, when it came, would shatter our understanding of reality itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper titled On the Electrodynamics of Moving Bodies. Albert Einstein had found the solution, and it was radical. Light speed is constant not because of some special property of light, but because space and time themselves are flexible. They stretch and compress to ensure light always travels at the same speed regardless of the observer's motion. The mathematics was elegant. If you move faster through space, you must move slower through time. The combined motion through space-time, the four-dimensional fabric of the universe, remains constant. We're all moving through space-time at the speed of light. When you sit still in space, all your motion is through time. When you move through space, some of that motion diverts away from time. This led to extraordinary predictions. Moving clocks tick slower. Moving rulers shrink. Two events simultaneous for one observer occur at different times for another observer in motion. There is no universal now shared by everyone in the universe. Einstein's equations were clear. Travel at 90% the speed of light and time slows to about 44% of its normal rate. At 99% light speed, time slows to 14%. At 99.9%, just 4%. Approach light speed, and time nearly stops. The scientific community was skeptical. These weren't minor corrections to Newtonian physics. They were fundamental reimaginings of reality itself. Einstein needed proof, and the universe provided it in spectacular fashion. In 1915, Einstein expanded his theory to include acceleration and gravity. General relativity predicted that gravity isn't a force pulling objects together, it's the curvature of space-time itself. Mass bends space-time, and objects follow the curved paths. This meant that gravity should affect time. The stronger the gravitational field, the slower time flows. Einstein calculated that light from the sun passing near its edge should bend by 1.75 arcseconds, about the width of a quarter seen from 2 miles away. Tiny but measurable. In 1919, British astronomer Arthur Eddington led expeditions to observe a total solar eclipse from Principio Island off Africa and Sobral, Brazil. During totality, with the sun's light blocked, they photographed stars near the sun's edge and measured their positions. The stars had shifted. Light had bent exactly as Einstein predicted. The announcement made headlines worldwide. Newton's 250-year reign had ended. Space and time were not absolute containers for the universe. They were dynamic participants in cosmic events. But the more profound implication, gravitational time dilation, would take decades to prove directly. In October 1971, physicists Joseph Haefel and Edward Keating did something extraordinary. They bought tickets on commercial airline flights circling the globe and brought with them 4 cesium atomic clocks, the most precise timekeeping devices available. Atomic clocks measure time by counting the oscillations of cesium atoms transitioning between energy states. These clocks were accurate to within a few billionths of a second per day. Haefel and Keating flew eastward around the world and then westward, while identical clocks remained at the U.S. Naval Observatory in Washington, D.C. According to relativity, 2 effects should occur. Clocks in motion should tick slower due to velocity time dilation, but clocks at altitude should tick faster because of weaker gravity. When they compared the clocks after the flights, the results matched Einstein's predictions within experimental error. The eastward flying clocks lost 59 nanoseconds compared to the ground clocks. The westward flying clocks gained 273 nanoseconds. Time dilation wasn't philosophical speculation, it was measurable reality. But these were just the opening movements of a symphony revealing time's true nature. The evidence was about to accumulate in ways no one anticipated. Cosmic rays, high-energy particles from space, constantly bombard Earth's atmosphere. When they collide with air molecules, they create showers of secondary particles, including muons. Muons are unstable particles. They decay in 2.2 microseconds when at rest. At the altitude where they're created, about 10 kilometers up, traveling at 99.8% the speed of light, they should decay long before reaching the ground. Simple mathematics. Traveling 10 kilometers at near light speed takes about 33 microseconds. But muons decay in 2.2 microseconds. They shouldn't make it. Yet they do. Detectors on Earth's surface measure thousands of muons every second. The explanation? Time dilation. From the muon's perspective, time passes normally. It still decays in 2.2 microseconds. But from Earth's perspective, the muon's internal clock runs slowly. At 99.8% light speed, time dilation increases the muon's lifetime by a factor of 15. Those 2.2 microseconds become 33 microseconds in Earth's reference frame, just enough time to reach the surface. Every cosmic ray detection is proof that time dilation is real. Thousands of experiments per second raining down from the sky. At CERN's Large Hadron Collider outside Geneva, protons race through a 27-kilometer ring at 99.999999991% the speed of light. At these velocities, time dilation increases the proton's lifetime by a factor of 7,500. Unstable particles that would normally decay in nanoseconds survive for microseconds, long enough to circle the accelerator thousands of times before disintegrating. Engineers must account for time dilation when designing the detectors. Without relativistic corrections, the particles would appear in the wrong locations. In 2017, physicists at the Relativistic Heavy Ion Collider in New York accelerated gold ions to similar speeds and measured their decay rates with unprecedented precision. The results matched special relativity's predictions to within 0.00002%. Every particle physics experiment conducted in the last 70 years confirms time dilation. The standard model of particle physics, our most successful theory of fundamental forces, is built on relativistic quantum field theory. Without time dilation, none of modern physics works. 24 satellites orbit Earth at an altitude of 20,200 kilometers, traveling at 14,000 kilometers per hour. Each satellite carries atomic clocks that broadcast precise timing signals. Your phone receives signals from multiple satellites and calculates your position based on the time differences. But there's a problem, or rather two problems. First, velocity time dilation. The satellites move at high speed relative to Earth's surface, so their clocks should tick slower than ground clocks by about 7 microseconds per day. Second, gravitational time dilation. The satellites orbit in weaker gravity than at Earth's surface, so their clocks should tick faster by about 45 microseconds per day. The net effect? Satellite clocks gain about 38 microseconds per day relative to ground clocks. That might sound insignificant, but light travels 30 centimeters per nanosecond. In 38 microseconds, light travels 11 kilometers. Without corrections for time dilation, GPS positions would drift by over 10 kilometers per day. Within a week, GPS would be useless. Engineers programmed the satellite clocks to tick at a different rate before launch, 10.23 megahertz instead of the ground-based 10.23 megahertz standard. This pre-compensation accounts for both velocity and gravitational time dilation. When the satellites reach orbit, their clocks synchronize perfectly with Earth's surface. Every time you use GPS navigation, you're betting your life on Einstein being right about time dilation. So far, he's never been wrong. In 1960, physicists Robert Pound and Glenn Rebka conducted an experiment in Harvard's Jefferson Tower. They placed a gamma-ray source at the top of a 22.5-meter tower and a detector at the bottom. Gamma rays are high-frequency photons, particles of light. As they fell through Earth's gravitational field, they should gain energy, just as a ball gains kinetic energy when dropped. But photons can't speed up. They always travel at light speed. Instead, they gain energy by increasing their frequency, shifting slightly toward the blue end of the spectrum. Pound and Rebka measured a blue shift of 2.5 parts in a quadrillion, exactly matching Einstein's prediction for gravitational time dilation over 22.5 meters. Think about that. Over just 22 meters of height difference, time flows measurably differently. Your head ages faster than your feet. The effect is tiny, about 90 billionths of a second difference over a human lifetime, but it's real. In 2010, physicists at the National Institute of Standards and Technology in Colorado measured gravitational time dilation over just 33 centimeters of height difference, using the world's most precise atomic clocks. They detected time dilation at the scale of a single stair step. Gravity doesn't just bend space, it warps time. The stronger the gravity, the slower time flows. On Earth's surface, time runs slower than in orbit. Near a black hole, time nearly stops from the perspective of a distant observer. White dwarfs are stellar corpses, the collapsed cores of dead stars, packing a sun's worth of mass into an Earth-sized sphere. Their surface gravity is about 350,000 times stronger than Earth's. When we observe light from white dwarfs, we see gravitational redshift. Photons climbing out of the intense gravitational field lose energy, their frequency shifting toward the red end of the spectrum. This redshift is distinct from the Doppler shift caused by motion. It's purely gravitational. In 2011, astronomers using the Hubble Space Telescope measured gravitational redshift from the white dwarf Sirius B with unprecedented precision. The redshift indicated that time on Sirius B's surface flows at 99.997% the rate of time far from any gravitational field, a slowdown of 0.003%. That might not sound dramatic, but consider, if you could stand on Sirius B's surface, you couldn't. The gravity would crush you instantly. For every hour that passed for you, an hour and 1 second would pass for someone far from any star. Over a year, you'd age 4 days less than distant observers. Neutron stars take this to extremes. These ultra-dense remnants pack 1.4 solar masses into a sphere just 20 kilometers across. Surface gravity exceeds Earth's by 200 billion times. Time dilation becomes severe. Time on a neutron star's surface flows at roughly 70 to 80% the rate of time in empty space. In 2019, NASA's NICER telescope observed X-ray pulses from the millisecond pulsar PSR 0030 plus 0451. By analyzing the pulse timing with extreme precision, astronomers measured the star's radius and mass and confirmed the time dilation predicted by general relativity in these extreme gravitational environments. At the edge of a black hole lies the event horizon, the point of no return where escape velocity equals light speed. Here, time dilation becomes infinite from the perspective of a distant observer. Imagine watching a clock fall toward a black hole. As it approaches the event horizon, it appears to tick slower and slower. Light from the clock becomes increasingly redshifted, dimmer and dimmer. The clock appears to freeze at the event horizon, its time essentially stopped from your perspective. But from the clock's perspective, time passes normally. It crosses the event horizon and continues toward the singularity, experiencing no special moment at the horizon itself. This creates a paradox. From outside, nothing ever crosses the event horizon. It freezes there eternally. From inside, crossing happens in finite time. Both perspectives are equally valid. There is no absolute truth about when or whether the clock crosses. This is the nature of time in relativity. It's not a universal river flowing uniformly everywhere. It's a local phenomenon, different for every observer depending on their motion and gravitational environment. In 2020, astronomers using the Event Horizon Telescope captured the first image of a black hole shadow in galaxy M87. The light forming that image had been bent by the black hole's gravity, traveling through regions of extreme space-time curvature, where time dilation reaches extraordinary values. Analyzing the image and the dynamics of matter orbiting the black hole, astronomers confirmed that time dilation near the event horizon matches general relativity's predictions. Matter in the innermost stable orbit, the closest you can orbit without falling in, experiences time at about 60% the rate of distant observers. Time dilation and quantum mechanics. Here's where things get truly strange. Time dilation isn't just a large-scale phenomenon. It affects quantum processes. In 2014, physicists at the University of Vienna conducted an experiment with entangled photons, pairs of light particles linked by quantum mechanics such that measuring one instantly affects the other regardless of distance. They sent one photon of each entangled pair through a region of stronger gravitational field while keeping the other in a weaker field. The time dilation difference was minuscule, just a few billionths of a second, but measurable. The results showed that quantum entanglement persists despite time dilation. The photons remained correlated even though they experience time at different rates. This suggests that quantum connections transcend space-time itself. They're somehow outside the time dilation effects that govern everything else. This has profound implications for quantum information theory. If you could create a network of quantum computers at different gravitational potentials, say one on Earth and one in orbit, they would experience time differently but could still share quantum information instantaneously through entanglement. But there's a deeper mystery. The measurement problem in quantum mechanics involves collapse of the wave function, an instantaneous process. But instantaneous relative to what? If time flows at different rates in different locations, what does it mean for something to happen instantly everywhere? Some physicists argue this suggests time isn't fundamental. It emerges from more basic quantum processes. In this view, time dilation isn't about time flowing at different rates. Rather, it's about different regions of space having different amounts of happening per unit of subjective experience. Today's atomic clocks are so precise they can detect height differences of 1 centimeter through gravitational time dilation. The NIST F2 atomic clock in Colorado is accurate to 1 second in 300 million years. But physicists aren't building these clocks just to measure time. They're searching for deviations from Einstein's predictions that might reveal new physics. In 2022, researchers at GILA in Boulder, Colorado, created an optical lattice clock using strontium atoms trapped by lasers that can detect gravitational time dilation over distances of just 1 millimeter. This precision enables testing general relativity at laboratory scales previously impossible. The experiments are searching for violations of Einstein's equivalence principle, the assumption that gravity and acceleration are indistinguishable. Some theories of quantum gravity predict tiny deviations from general relativity at small scales. If different types of particles experience time dilation slightly differently, these clocks would detect it. So far, no deviations have been found. General relativity remains undefeated. But these clocks have revealed something unexpected. Time is noisier than we thought. At extremely short timescales, femtoseconds, quadrillionths of a second, quantum fluctuations in the fabric of space-time create tiny variations in time's flow. This temporal foam represents the boundary where quantum mechanics and general relativity meet. Physicists believe that understanding this quantum noise in time might provide clues to reconciling relativity with quantum mechanics, the holy grail of theoretical physics. The evidence is overwhelming. Time isn't absolute. It's not a fixed stage on which events play out. It's a flexible, dynamic dimension that bends, stretches, and flows at different rates depending on motion and gravity. But this raises profound questions about causality, free will, and the nature of existence itself. If time dilation is real, if different observers experience time at different rates and disagree about simultaneity, what does that mean for the nature of time itself? One answer is eternalism, also called the block universe theory. In this view, past, present, and future all exist equally. Time is like space, a dimension you can move through, with all moments existing simultaneously in a four-dimensional block. Your entire life, from birth to death, exists as a world line through space-time, a continuous path through the block universe. The present moment is just your current cross-section of this four-dimensional structure, like a flashlight beam illuminating one part of a landscape. This resolves the relativity of simultaneity. There's no universal now, because all moments exist eternally. When we say events are simultaneous, we are merely describing events that lie on the same three-dimensional slice through the four-dimensional block, and different observers slice the block at different angles. Many physicists find this view compelling because it takes relativity seriously. If different observers disagree about which events happen now, then now isn't a fundamental property of the universe. It's a subjective experience. But this creates a disturbing implication. If the future already exists in the block universe, is free will an illusion? Are we merely experiencing the unfolding of a predetermined path through space-time? Time dilation is intimately connected to a fundamental law. Nothing can travel faster than light. But why? The answer emerges from causality, the principle that causes must precede effects. If information could travel faster than light, time dilation would allow violations of causality. Here's how it works. Imagine two observers moving relative to each other. Due to relativity of simultaneity, they disagree about which events happen first. If you could send a faster-than-light signal from one event to another, one observer would see the signal arrive before it was sent. Effect preceding cause. Worse, you could create a causality loop. Send a faster-than-light signal forward in time from your perspective. Have someone else bounce it back with their own faster-than-light signal and receive your own message before you sent it. You could send yourself messages from the future. The universe prevents this by making faster-than-light travel impossible. The speed of light isn't just the speed of light. It's the speed of causality, the rate at which cause and effect propagate through space-time. This connects time dilation to the structure of reality itself. Time dilation exists because the universe enforces causality. The speed of light limit exists because time must be flexible. They're two aspects of the same fundamental principle. The twin paradox is relativity's most famous puzzle. One twin travels near light speed and returns younger than their sibling who stayed home. But relativity says all motion is relative. From the traveling twin's perspective, Earth moved away and returned. So shouldn't the stay-at-home twin be younger? The resolution involves acceleration. The traveling twin must decelerate, turn around, and accelerate back toward Earth. This acceleration breaks the symmetry between the twins. During the turnaround, from the traveling twin's perspective, the Earth twin rapidly ages. This happens because acceleration changes which distant events are simultaneous with the traveler. When you accelerate, your plane of simultaneity, the set of distant events you consider to be happening now, tilts in space-time. In 2005, physicists at the University of Maryland simulated the twin paradox using trapped ions, single atoms manipulated by lasers and electric fields. They accelerated one ion back and forth while keeping another stationary. After thousands of oscillations, the moving ion's internal clock lagged behind the stationary ion's clock by billionths of a second, exactly as relativity predicted. The twin paradox isn't a paradox at all. It's a prediction that's been verified countless times. Travel fast enough for long enough, and you genuinely age less than those who remain stationary. In 1963, mathematician Roy Kerr discovered a solution to Einstein's equations describing rotating black holes. These Kerr black holes have properties even stranger than non-rotating ones. A rotating black hole drags space-time itself into rotation, an effect called frame dragging. Near the event horizon, space rotates so fast that nothing can remain stationary. Even light beams get swept along with the rotating space-time. This creates a region called the ergosphere, outside the event horizon, where time becomes mixed with space in bizarre ways. The future direction, the direction time flows, has a spatial component. You can't help but orbit the black hole even if you fire your engines directly away from it. In 2004, NASA's Gravity Probe B satellite measured frame dragging around Earth. Our planet's rotation drags space-time like a ball spinning in honey, twisting the fabric of reality by tiny amounts. The effect is minuscule. Earth rotates space-time by about 39 milliarc-seconds per year, but the satellite's gyroscopes detected it. For stellar mass black holes rotating near their maximum rate, frame dragging becomes extreme. At the inner edge of the ergosphere, time dilation combined with frame dragging means that completing one orbit takes infinite time from the perspective of distant observers, yet takes finite time from a local perspective. You could orbit a fast-spinning black hole, experience hours, and return to find thousands of years have passed elsewhere in the universe. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating. But those observations relied on another form of time dilation, cosmological time dilation. When we observe a supernova 10 billion light-years away, we see it as it was 10 billion years ago. But due to cosmic expansion, space-time has stretched during the light's journey. This stretching affects time itself. Distant supernovae don't just appear fainter, they appear to explode in slow motion. A supernova that brightens over 20 days in its own reference frame appears to brighten over 40 days when observed from Earth if the light traveled through enough expanding space. In 2001, astronomers confirmed this by observing dozens of distant supernovae at various redshifts. The time dilation factor matched cosmological predictions perfectly. The universe's expansion literally slows down time for distant objects as observed from Earth. This means the early universe experienced time differently than we do now. In the dense, hot universe shortly after the Big Bang, processes occurred at different rates than we observe locally. The cosmic microwave background radiation we detect has been stretched, not just in wavelength, but in time. The photon's oscillations slowed by the expansion of space. Cosmic strings are hypothetical one-dimensional defects in space-time, remnants from the early universe when different regions underwent phase transitions. If they exist, they're incredibly dense. A cosmic string 1 meter long could have the mass of Earth. The space-time around a cosmic string is flat in one direction, but curved in the other, creating exotic geometries. Time dilation near cosmic strings produces strange effects. If you traveled around a cosmic string in one direction and returned to your starting point, you'd find you'd arrived before you left, a closed time-like curve. You'd emerge in your own past. This doesn't violate causality in the usual sense, but it creates the possibility of temporal paradoxes. Stephen Hawking proposed the chronology protection conjecture. The laws of physics prevent the formation of closed time-like curves, except possibly on microscopic scales. Quantum effects might create enough energy density near would-be time machines to destroy them before they can function. No cosmic strings have been definitively observed, but gravitational wave detectors like LIGO could detect them if they exist. A cosmic string oscillating and creating gravitational waves would produce a distinctive signature. If cosmic strings exist and are traversable, they represent the universe's ultimate test of causality and time's nature. In 1994, physicist Miguel Alcubierre discovered a solution to Einstein's equations that allows faster-than-light travel without violating relativity. The Alcubierre drive contracts space-time in front of a spacecraft and expands it behind, creating a warp bubble that carries the ship faster than light while the ship itself remains stationary within its bubble. Inside the bubble, time passes normally, but the bubble's creation and motion through space require exotic matter with negative energy density, something never observed and possibly forbidden by quantum mechanics. If an Alcubierre drive were possible, time dilation effects would be extraordinary. A ship could travel to a star 100 light-years away, experience only days or weeks, and return to find Earth has aged only slightly, bypassing the usual time dilation from high-speed travel. But there's a catch. When the ship decelerates and the warp bubble collapses, all the radiation and particles that accumulated in the bubble's event horizon are released in a catastrophic burst, potentially destroying anything in front of the ship. Current research suggests the energy requirements for an Alcubierre drive are astronomical, equivalent to converting Jupiter's mass entirely into energy. Even optimistic revisions require the mass energy of several suns. Warp drives remain speculative, but they illustrate how seriously physicists take Einstein's equations. If the mathematics allows something, we must consider whether the universe permits it, and what the implications would be for time's nature. In 1963, mathematician Roy Kerr discovered a solution to Einstein's equations describing rotating black holes. These Kerr black holes have properties even stranger than non-rotating ones. A rotating black hole drags space-time itself into rotation, an effect called frame dragging. Near the event horizon, space rotates so fast that nothing can remain stationary. Even light beams get swept along with a rotating space-time. This creates a region called the ergosphere, outside the event horizon, where time becomes mixed with space in bizarre ways. The future direction, the direction time flows, has a spatial component. You can't help but orbit the black hole even if you fire your engines directly away from it. In 2004, NASA's Gravity Probe B satellite measured frame dragging around Earth. Our planet's rotation drags space-time like a ball spinning in honey, twisting the fabric of reality by tiny amounts. The effect is minuscule. Earth rotates space-time by about 39 milliarc-seconds per year, but the satellite's gyroscopes detected it. For stellar mass black holes rotating near their maximum rate, frame dragging becomes extreme. At the inner edge of the ergosphere, time dilation combined with frame dragging means that completing one orbit takes infinite time from the perspective of distant observers, yet takes finite time from a local perspective. You could orbit a fast-spinning black hole, experience hours, and return to find thousands of years have passed elsewhere in the universe. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating. But those observations relied on another form of time dilation, cosmological time dilation. When we observe a supernova 10 billion light-years away, we see it as it was 10 billion years ago. But due to cosmic expansion, space-time has stretched during the light's journey. This stretching affects time itself. Distant supernovae don't just appear fainter, they appear to explode in slow motion. A supernova that brightens over 20 days in its own reference frame appears to brighten over 40 days when observed from Earth if the light traveled through enough expanding space. In 2001, astronomers confirmed this by observing dozens of distant supernovae at various redshifts. The time dilation factor matched cosmological predictions perfectly. The universe's expansion literally slows down time for distant objects as observed from Earth. This means the early universe experienced time differently than we do now. In the dense, hot universe shortly after the Big Bang, processes occurred at different rates than we observe locally. The cosmic microwave background radiation we detect has been stretched, not just in wavelength, but in time. The photon's oscillations slowed by the expansion of space. Cosmic strings are hypothetical one-dimensional defects in space-time, remnants from the early universe when different regions underwent phase transitions. If they exist, they're incredibly dense. A cosmic string 1 meter long could have the mass of Earth. The space-time around a cosmic string is flat in one direction, but curved in the other, creating exotic geometries. Time dilation near cosmic strings produces strange effects. If you traveled around a cosmic string in one direction and returned to your starting point, you'd find you'd arrived before you left, a closed time-like curve. You'd emerge in your own past. This doesn't violate causality in the usual sense, but it creates the possibility of temporal paradoxes. Stephen Hawking proposed the chronology protection conjecture. The laws of physics prevent the formation of closed time-like curves, except possibly on microscopic scales. Quantum effects might create enough energy density near would-be time machines to destroy them before they can function. No cosmic strings have been definitively observed, but gravitational wave detectors like LIGO could detect them if they exist. A cosmic string oscillating and creating gravitational waves would produce a distinctive signature. If cosmic strings exist and are traversable, they represent the universe's ultimate test of causality and time's nature. In 1994, physicist Miguel Alcubierre discovered a solution to Einstein's equations that allows faster-than-light travel without violating relativity. The Alcubierre drive contracts space-time in front of a spacecraft and expands it behind, creating a warp bubble that carries the ship faster than light while the ship itself remains stationary within its bubble. Inside the bubble, time passes normally, but the bubble's creation and motion through space require exotic matter with negative energy density, something never observed and possibly forbidden by quantum mechanics. If an Alcubierre drive were possible, time dilation effects would be extraordinary. A ship could travel to a star 100 light-years away, experience only days or weeks, and return to find Earth has aged only slightly, bypassing the usual time dilation from high-speed travel. But there's a catch. When the ship decelerates and the warp bubble collapses, all the radiation and particles that accumulated in the bubble's event horizon are released in a catastrophic burst, potentially destroying anything in front of the ship. Current research suggests the energy requirements for an Alcubierre drive are astronomical, equivalent to converting Jupiter's mass entirely into energy. Even optimistic revisions require the mass energy of several suns. Warp drives remain speculative, but they illustrate how seriously physicists take Einstein's equations. If the mathematics allows something, we must consider whether the universe permits it, and what the implications would be for time's nature. Time dilation tells us that time flows at different rates depending on motion and gravity. But it doesn't explain why time has a direction, why we remember the past but not the future, why eggs break but don't unbreak, why entropy increases. The laws of physics are time-symmetric. If you recorded any physical process and played it backward, it would still obey the fundamental equations. Yet we experience time flowing in one direction only. The answer might lie in thermodynamics and entropy. The second law of thermodynamics states that entropy, disorder, increases over time in closed systems. This provides time with an arrow, a direction, from low entropy to high entropy. But here's the puzzle. If the fundamental laws are time-symmetric, why does entropy increase? Why was entropy low in the early universe? Some physicists argue that the Big Bang itself is responsible. The universe began in an extraordinarily low entropy state, highly ordered, with matter and energy distributed smoothly. As it evolved, entropy increased, creating the arrow of time we experience. Others suggest that time's arrow is an illusion of perspective. In the block universe, all moments exist eternally. The flow of time is just our consciousness moving along our world line, experiencing higher entropy states after lower entropy states. Time dilation doesn't explain the arrow of time, but it constrains theories that attempt to. Any explanation for time's direction must be compatible with time's relativity. At the Planck scale, 10 to the minus 35 meters and 10 to the minus 43 seconds, quantum effects dominate space-time itself. Here, the smooth fabric of space-time Einstein described breaks down into quantum foam, a seething chaos of virtual black holes and wormholes appearing and disappearing. At these scales, time might not be continuous. It might come in discrete chunks, chronons, the smallest possible units of time. Below the Planck time, the concept of before and after might lose meaning entirely. Some approaches to quantum gravity, like loop quantum gravity, suggest space-time is fundamentally discrete. Time isn't a smooth dimension, it's pixelated, quantized into Planck time intervals. Other approaches, like string theory, require additional dimensions of time, or allow time to emerge from more fundamental geometric structures. In these theories, time isn't fundamental, it's an approximate concept that emerges at large scales from deeper mathematical objects. If time emerges rather than being fundamental, then time dilation represents a macroscopic approximation breaking down at the quantum scale. Asking what happens before the Planck time becomes meaningless, like asking what's north of the North Pole. This suggests that time itself might end in extreme conditions. At a black hole singularity, time might cease to exist. In the Big Bang's first instant, time might not yet have emerged. Time has boundaries, beginnings, and possibly ends. Time dilation forces us to confront the subjective nature of reality. There is no universal clock, no absolute time, no objective now shared by everyone. Two observers moving relative to each other genuinely experience time differently. Neither is wrong. Both perspectives are equally valid. Reality itself depends on the observer. This philosophical shift parallels quantum mechanics' measurement problem. In quantum theory, observation affects reality. Particles exist in superposition until measured. In relativity, motion affects reality. Events' temporal order depends on the observer. Perhaps reality isn't objective at all. Perhaps it's fundamentally relational, defined not by absolute properties, but by relationships between observer and observed. This view suggests consciousness might play a more fundamental role in physics than previously thought. Not that consciousness creates reality through mystical means, but that the concept of observer is essential to defining what we mean by physical reality. Time dilation proves that your experience of duration is as real as anyone else's, even when it conflicts with theirs. You're not experiencing an illusion. You're experiencing your own equally valid slice through space-time's four-dimensional structure. For most of human history, we assumed everyone experienced time identically. Clocks might be inaccurate, but time itself flowed uniformly for all. Now we know better. Every time you climb stairs, you age faster than someone below. Every time you drive, your watch ticks slower than stationary clocks. These effects are tiny, billionths of a second, but real. Astronauts on the International Station age about 0.007 seconds less per 6-month mission than people on Earth. Russian cosmonaut Sergei Krikalev, who spent 803 days in space over multiple missions, has aged about 0.02 seconds less than if he'd remained on Earth. He's the farthest time traveler in human history. He's been to everyone else's future by 0.02 of a second. As we venture deeper into space, time dilation will become practically significant. A crewed mission to Mars would experience measurable time dilation. Colonists on Mars would age at a different rate than Earth, slightly faster, due to Mars's lower gravity. If we ever achieve near light-speed travel, the implications become profound. A journey to a nearby star and back could be months for travelers, but decades or centuries for Earth. Families would be separated not by distance, but by time itself. Time dilation isn't just theoretical, it's engineered into our technology. GPS satellites, particle accelerators, astronomical observations, and precision timekeeping all account for relativistic effects. Future technologies will exploit time dilation deliberately. Particle physicists already use it to extend unstable particle lifetimes for study. Quantum computers in orbit could leverage time dilation for novel computational approaches. Some theorists propose using time dilation for data storage. Encode information in particles moving at different relativistic speeds, storing data in the time dimension itself. More speculatively, if we develop fusion rockets or antimatter drives capable of reaching significant fractions of light speed, interstellar travel becomes possible within a human lifetime for the travelers. Time dilation becomes humanity's key to reaching the stars. We began this journey with 2 twins and atomic clocks on airplanes. We've traveled through the mathematics of space-time, the observations confirming Einstein's predictions, the exotic physics of black holes and cosmic strings, and the philosophical implications of time's flexibility. Time is not what we thought it was. It doesn't flow uniformly. It bends around massive objects. It slows with motion. It's fundamentally relative, different for each observer depending on their path through space-time. Every clock ticks at its own rate. Your head ages faster than your feet. GPS satellites experience time differently than you do. Astronauts travel to the future, even if by mere fractions of seconds. The scientific consensus is unambiguous. Time dilation is real, measured and woven into the fabric of reality. Special and general relativity have been tested in every conceivable way and have never failed. Time's flexibility isn't speculation, it's established fact. Yet mysteries remain. How does time dilation reconcile with quantum mechanics at the Planck scale? Is time fundamental or emergent? Does the block universe mean the future already exists? Can causality truly be preserved at all scales? These questions drive current research. The next generation of atomic clocks, gravitational wave detectors, and space-based observatories will probe time's nature with unprecedented precision. We may discover that time is even stranger than Einstein imagined. Time flows differently for each of us, not metaphorically, but physically, measurably, undeniably. The clock in your hand ticks at a different rate than a clock on a mountain, a clock in orbit, a clock near a black hole. You are moving through space-time at your own unique pace. Your personal time is as real as anyone's, even when it contradicts theirs. We are all time travelers, moving through the fourth dimension at our own individual speeds, each experiencing our own private flow of moments, each on our own journey through the infinite landscape of space-time. The universe is vast. The mysteries are endless. Time itself is the deepest mystery of all. But remember this: every second you experience is uniquely yours. Time, in the end, is personal.